first thing I do for problems like this is I just go ahead and make a chart. Whenever I get a chart, I just draw a picture so I can better visualize what's going on. 15, so the 15 down here represents the time. Let's see here, 67.9 is, what does W represent? The temperature of the water in the tub. Okay, and then right up here, T is 20, we've got a 71. And it says T is increasing, twice differentiable, and temperature is 55 at 0. Water is heated for 30 minutes beginning at time T equals 0. 30 minutes, and values of, okay, so we've got the temperature at selected times for the first 20 minutes. Alright, so we're supposed to try to find W prime 12, so the derivative of W at 12. Use the data in the table. Alright, so the derivative at 12, if we draw a line right here, right there, 12 is right in between. So we're supposed to try to find W prime at 12. Well, the W prime at 12 is the slope right there. Well, the slope right there, oh great, hold on. So what I'm going to try to do here is help you guys understand kind of how to interpret the problem. I know at first you think maybe this isn't so easy to understand, but again, when I draw a picture, it makes it much more easy for me to kind of figure out what's going on. If we only get this amount of data, we're given 5 pieces of data, W prime of 12. Now remember, W is, let's see if I can use this, W is just this curve. That's a bad color here. W could be going up like this. We don't really know what W is. This is our graph of W of T. And since we don't really know what the graph is, let's see, we could look like this. It could come down here and go up and then say constant like that. But again, we don't know what it is. We're only, and it says estimating. Use the data in the table to estimate W prime. And W prime is the slope of the curve in between, well, the slope of the curve at any point, but W prime of 12 is the slope of the curve right there in between these two values. And the only data we have to go by is a line segment that we would draw in between, just like I did here, in between these 2 points. And so anyway, W prime of 12 would be the Y value, 69.9, difference in the Y values I should say, minus 61.8 all over the difference in the X values, 15 minus 9, and don't do anything but put a box around that. If it's asking for units, it says using correct units, so it is asking for units. And let's see, water temperature is increasing at a rate of approximately, so this is degrees Fahrenheit, so I want to make sure I get this right, degrees Fahrenheit, and T is in, what is that, minutes? Yeah, that's in minutes. Okay, and so we would say the water's increasing at a rate, hold on a second, computation of use correct units, interpret the meaning of your answer. Okay. That would mean the water temperature is increasing at a rate of this. That would be degrees Fahrenheit per minute. Okay? Degrees Fahrenheit per minute. And that's it. So that's part A. That is part A. And then part B, I don't know if I can squeeze it in here, but I'll give it a shot. So part B, for 0 to 20, average temperature of the water is, so it gives you that, so we could actually even do that. W, average temperature of the water, right there. Okay, 0 to 20. All right, average temperature. Use a left Riemann sum with the 4 subintervals indicated to approximate that value. Okay, so left Riemann sum. Well, left Riemann sum means that we're going to draw rectangles like that. Okay, and 4 subintervals. It says it's increasing, and remember LRAM, just wanted to reiterate this, we had that LRAM is too low when the function is increasing, RRAM is too high. This is that visual I gave you guys. LRAM is too low, so our LRAM is going to be too low because it says that this function is increasing. Okay. So over the interval, hold on. Sorry, I was answering part C. So let's actually just change this to part C so I can do that first, since I already started that part. Left Riemann sum, 4 subintervals. So basically what we're going to do here is we're going to find the area of each of these guys. This will be 4 times 55. So the dimensions here are 4 here and 55 along there. So 4 times 55. And then this one will be 5 times 57.1. Over here, this is 6 times 61.8. And you get the idea, hopefully. And over here, this is 5 multiplied by 67.9. Okay, so anyway, you just find the areas of each of those guys and you get the LRAM. So LRAM, and then you would put all those numbers in there. And don't try to simplify that, you can leave it alone. And let's see, approximate that. Does it overestimate or underestimate? Well, the average temperature of the water, well, it would underestimate because the left Riemann sum is used and it says the function is increasing like we said. So for part C, that's an underestimate. Okay, so I'm going to switch over to part B on the other side. Okay, so for part B, it says, let's see here, evaluate 0 to 20 of W prime, okay, dt, and use the data in the table to evaluate that. Okay, well, we don't really have anything in regards to WT, but if we just think back to the fundamental theorem of calculus, we know that the antiderivative of W prime is W, okay, and when we use the second part of the fundamental theorem of calculus, we know that we take our antiderivative and evaluate that at the upper limit, and we subtract from that the antiderivative evaluated at the lower limit. And we know that W20 is given to us, and that's 71. W at 0 is 55, and that gives us 16. And it says using correct units. And so what would that mean? It would mean that think about a picture of this whole thing happening. We've got the function going up like that. We integrate the derivative, and that would give us the rate at which the temperature is changing. And from 0 to 20, it would give us the total change in temperature as a positive number. So if this is W prime, then it says 16 then would be the area. Right? So 16 is the area of that region, W prime. W prime would be degrees Fahrenheit per minute, and when we integrate, we just get the degrees Fahrenheit. So the degrees Fahrenheit, 16 degrees Fahrenheit change, or I should say the water has warmed up by 16 degrees Fahrenheit in the first 20 minutes. So from T equals 0 to T equals 20. The temperature is warmed by 16 degrees. Alright, so here's the deal with part D. It says from 20 to 25 we've got a first derivative W given by, okay, I won't write that down, you know what it is, and I'm going to let that be my Y1, by the way, on my calculator, because it's asking us to find the temperature of the water at time equals 25. So we want the temperature, and we know the rate of change of the temperature, and this should be solid right now. You guys should be solid with this. If you want temperature, you want the current amount, and you know the rate of change of that, then you just set up this integral, because we know the rate of change at 20, and this is, again, it's going from 20 to 25. Okay, you can't use 0 here. Okay, don't use 0, because it's not changing from 0 to 25, it's changing from 20 to 25. That's the information it gave us. So, so we want to put 20 to 25, and then we put our W prime of T right there. And this is an easy thing to find because we use our calculator. Okay, and this guy is already given to us as 71, and so all we have to do is add 71 to this guy, and we get our W of 25. So we get our temperature at 25 using that equation is about 73.043. Okay, so good to go there. We're getting close, less than 2 weeks away.